All right, today we're going to be looking at acceleration, definition, units, what does it look like graphically, how do we solve it, and then how do we connect, the acceleration of a object to distance. So let's start with the definition. So acceleration is the change in velocity per unit time. Okay, change in velocity per unit time. Most commonly, our units are meters per second, or really meters per second squared. You could have other units of acceleration, but in physics, most commonly it's meters per second squared. So a quick note though, that acceleration is a vector quantity, okay? Which means that it has both magnitude, and by magnitude, I mean a number with a unit, okay? So magnitude meaning a number, and direction. North, south, west, up, down, either of those. So therefore, a change in either the magnitude, meaning the number, or the direction causes a change in acceleration. That's a C. That's important to note because we often think of just a change of acceleration for magnitude, but it also is for a change in direction. So graphically, okay, let's think about what this would be. So think about what the object is doing and measuring how that object's motion changes. So a quick note about all of these graphs, they are all versus time. So I'm going to add that note at the bottom. So they're all versus time. And make a note also that a flat line means that something is constant. So for this first one, constant displacement, we've got a flat line for distance and a flat line for velocity because it's staying still, it's constant. And then any other time that we have a flat line, it's looking at something that's constant, especially in terms of our velocities here. I'm going to draw like a little dotted line to separate these because everything this direction has acceleration. And that's because we have a change in our velocity. So in a distance time graph, that's going to look parabolic, okay? So it's speeding up or it's slowing down, and then either in a positive or negative direction. And then how this parabolic shape translates into a velocity time is going to be a flat line, but not horizontally flat, meaning zero. You're going to be able to get a slope from this. And so the slope of these lines, and we can do that with just, rise, run, x2, x1, oops, sorry, that's the wrong way. y2 minus y1, whatever, that's going to give us our acceleration. So take note, there are positives and negatives in terms of our velocity. And again, that's because we either have a change in our magnitude or a change in our direction. And depending on the shape of the parabolic curve, it's telling us if we're slowing down or speeding up. And again, you can determine the acceleration of delta V over delta T, just like you would in like a math class. So M being your slope is your delta Y over delta X. You can see the parallels there. You're solving for it the same way. So that's just a glance of what it would look like graphically. This is a really great image in terms of defining what's happening. And if you look at the motion of these objects here, it's giving you a visual of what's happening in terms of how that object is moving. So if we're going to look at this mathematically, let's move my paper up. We've got an equation of our acceleration as our change in our velocity over our change in time. So note we have got our change in velocity is our final velocity minus our initial velocity, and our change in time is our final time minus our initial time. So let's do a couple of example problems and see if we can solve. I think the hardest part about solving problems in this class is just recognizing what you've got and identifying what variable they stand for. Okay, so number 1, a car traveling west. So that's important because it tells us our direction. At 60 meters per second, so I'm going to underline it because that's what I'm given. And then it accelerates to 90 meters per second in 3 seconds. So I'm underlining all of these things because it's what's given to me in the problem. And then the question asks, what is the car's acceleration? So I'm going to circle it. Above it, I'm going to write what variable I'm using here, so that way when I list my variables and I solve, it becomes a lot easier. So acceleration, I'm going to label for A. This 60 meters per second is my initial velocity, okay, because I can read that based on how the problem is worded. So at 60 meters per second to 90 meters per second. So this is my final velocity. And I'm using V0 or V0 as my notation for my initial velocity and VF for my final velocity. And then 3 seconds is my delta T. Now it says delta T is change in time or final minus initial, but in this case it doesn't really give me a initial, it just tells me the total change in, so that's my delta T. So that right there is, I think, one of the hardest parts about these problems is just identifying your variables. So now let's list it out. Acceleration equals, I don't know, that's what I'm looking for. My initial velocity is 60 meters per second. My final velocity is 90 meters per second. And my delta T is 3 seconds, okay? So in order to solve, acceleration equals my final velocity, 90 meters per second, minus my initial, 60 meters per second, divided by my time, which is 3 seconds. So 90 minus 60 is 30 meters per second, divided by 3 seconds. So then I know that 30 divided by 3 is 10. So my acceleration is 10 meters per second squared, because it's per second per second. Okay, they don't cancel. It's per second per second. And then because acceleration is a vector quantity, I need a direction. And in the problem, it tells me I'm heading west. So I'm going to do a capital W. So in number 1, my answer is that my acceleration is 10 meters per second squared west. All right, let's take a look at number 2. A car traveling north, that tells me a direction, at 30 kilometers per hour slams on the brakes to avoid an accident. The car comes to a safe stop at 6 seconds after applying the brakes. What is the car's acceleration? Okay, so I know that I'm looking for acceleration again, so I'm going to put an A next to it. I have a direction. This 30 kilometers per hour is my initial velocity. And I know it's my initial velocity because of how the question is written, okay? And it comes to a stop. So if it's coming to a stop, then that would tell me my final velocity because it's stopping, meaning it's no longer moving, which means my velocity would be 0. And then my 6 seconds, again, tells me my delta T. So acceleration equals, I don't know, I'm looking for it. My initial velocity is 30 kilometers per hour. And you can write it like this, you can write it like this, you can do km per h. It's all pretty much the same thing. It just depends on what is preferred by whomever is teaching. And then final velocity is 0 kilometers per hour. And I know it's 0 because it comes to a stop. And my delta T is 6 seconds. So now let's plug it in. So my acceleration is going to equal my final velocity, which is 0 kilometers per hour, minus my initial, which is 30 kilometers per hour, divided by my time, which is 6 seconds. Okay, so for this one, I've got negative 30 kilometers per hour divided by 6 seconds. So it's negative because 0 minus 30 is negative 30. Okay, and note it's traveling at 30 kilometers per hour and then stops. So it's decelerating, or it's slowing down, which is how I end up with a negative here. So 30 divided by 6 is -5 kilometer per hour per second. Okay, now that is kind of a weird unit, but the unit still stands, it still works, because we're talking about how much are we slowing down in terms of kilometers per hour every second. So this is an acceptable unit. It's a little wonky. We're used to meters per second even, but it's still an acceptable answer in terms of your units. So it's -5 kilometers per hour per second north. And I'm just going to do a capital N underneath, and that is my answer. So it's decelerating, or it's slowing down at 5 kilometers per hour every second in the northern direction. Number 3. An object speeds up to 45 meters per second south in 5 seconds with an acceleration of 2 meters per second. What is its initial velocity? So this is a little different than number 1 and number 2. So again, the hardest thing is just identifying what you've got. So an object speeds up to 45 meters per second. So that tells me that this is my final velocity based on how it's written. In 5 seconds, so this is my delta t, with an acceleration of 2 meters per second. So I'm going to write A for acceleration. And what is its initial velocity? So I'm going to write V0 or V0 because that is what I'm looking for. Okay, so here we go. Acceleration equals 2 meters per second squared. That's what I've identified here. My initial velocity, I don't know. That's what I'm looking for. My final velocity is going to be 45 meters per second. And my delta t is 6 seconds. Okay, there's a couple of ways that you can solve this. What I'm going to do is I'm going to show you the equation. I'm going to talk you through rearranging it all, and then we're going to plug it in so it's easy to find an answer at one time. Okay, so acceleration equals, looking at this equation up here, my delta v is your final velocity minus your initial. So I'm going to say it's my final velocity minus my initial divided by delta t, or your time. So I'm going to try to get V0 or initial velocity by itself before I plug in. Okay, you can plug it in and then solve, it's up to you. But I'm just going to show you through, or walk you through rearranging it. So I'm going to multiply by delta t on both sides just to get rid of it. Okay, so these will cancel. So now I'm going to have my acceleration times my, I'm just going to drop the delta and write time. So my acceleration times time equals my final velocity minus my initial. So I want this one by itself, so I'm going to subtract out my final velocity from both sides. And I'm going to have my acceleration times time minus my final velocity equals negative of my initial velocity. Okay, so this negative here is something we can get rid of by dividing by -1 or multiplying by -1 for the whole thing, just like we would in a math class. So I'm going to multiply by -1, and that's going to flip this side and give me a positive V0 here. So my initial velocity equals my final velocity minus acceleration times time. And this is the equation I'm going to use to plug my numbers in to solve for V0. So initial velocity equals my final velocity, so 45 meters per second, minus my acceleration, which is 2 meters per second squared, times my time, which is 6 seconds. Okay. Oh my gosh, I'm saying 6 and I mean to say 5. Hold on, pause. Okay, sorry about that. I had been writing 6 and I mean to write 5. My apologies. So I'm just going to fill this back in with 5. So one more time, this is supposed to be 5 seconds and not 6 because that is what's in my question. Sorry about that. That's my fault. So now let's keep solving. So we've got 45 meters per second minus, we're going to solve this first. So 2 times 5 is 10. And then our seconds will cancel with one of these seconds squared. So we would just end up with meters per second as our units. So that's 10 meters per second is what I solved here. So then 45 meters per second minus 10 meters per second is 35 meters per second. And we're heading south, and that is my initial velocity. So this object was heading 35 meters per second south, and then it sped up in 5 seconds with an acceleration of 2 meters per second to then have a speed or a velocity of 45 meters per second. Okay, let's go ahead and flip this up and connect. Ooh, I'm upside down. And let's go ahead and connect our distance with our acceleration. Okay, so let's say then you have an acceleration of an object and you need to know how far that object has gone in a specific amount of time, and we can use this equation. We have used all of these before, and now it's just a matter of plugging it in and identifying what we've got to see how far that object has gone. So we've got distance equals my initial velocity times the time that it's traveled plus 1/2 of its acceleration of time squared. Okay, so here we go. If a car stopped at a stoplight begins traveling at 3 meters per second squared, okay, so that's my acceleration, for 3 seconds, after the light turns green, how far has it traveled? Okay, so it stopped at a stoplight. So that is my initial velocity because I'm stopped. So whenever I'm stopped at a stoplight, my initial velocity is 0. It's traveling at 3 meters per second squared. If you're not sure if this is velocity or acceleration, look at the units. If you've got a squared here, then that's going to tell you it's acceleration. And 3 seconds is my time. And how far it's traveled is my distance. So the hardest part about these questions is just figuring out what the units are. So let's go ahead and list them and see what we've got. Distance, I don't know. My initial velocity is 0 meters per second. If you're not sure what the units are, take a look at your acceleration, and then you're going to use similar units. So velocity is going to be meters per second. And my acceleration is 3 meters per second squared, with my time being 3 seconds. So now I just plug it in. Distance equals my initial velocity, so 0 meters per second, times my time, which is 3 seconds, plus 1/2 of my acceleration, which is 3 meters per second squared, times 3 seconds squared. Okay, so all I did was plug in what I've got into this equation right there. All right, so now let's just go stepwise to solve. Distance equals 0 times 3 is 0. Seconds and seconds cancel. So 0 meters plus 1/2 3 meters per second squared. I'm going to square this. So 3 squared is 9, and second squared is second squared. Okay, my next step is I'm going to be looking at this one. So seconds squared cancels with seconds squared. So now my distance is going to equal 0 meters plus 1/2 of 3 times 9, which is 27 meters. Okay, so now I'm going to be looking at, well, what is 1/2 of 27? So you can just multiply 1/2 times 27, or 27 divided by 2. So my distance is 13.5 meters. Okay, so this object has traveled 13.5 meters in 3 seconds from stop with an acceleration of 3 meters per second squared. And that is acceleration, looking at it graphically, solving some problems, and also determining the distance when given an acceleration.